Hello there, curious minds. Ever wondered why water fills up your glass perfectly, but a rock just keeps its shape no matter what? Well, that's the fascinating world of fluids for you. Here's a little joke to get us started. Why did the fluid break up with the solid? Because it just couldn't handle the pressure of staying rigid. Fluids are substances that can flow. That means they don't hold a fixed shape like solids do. Both liquids, like water, and gases, like air, belong to this wonderful family because they move and spread out to fit their containers. Now, what's happening at the molecular level? Unlike solids, where molecules are tightly packed and locked in place, fluids have their molecules arranged loosely with weaker intermolecular forces. That's why they simply take the shape of whichever container you pour them into. They just can't say no to fitting in. When we describe fluids in physics, especially in thermodynamics, we focus on key parameters: pressure, which we call P, volume marked as V, temperature noted by T, and density symbolized by the Greek letter ρ. Here's the formula for density: ρ equals mass divided by volume, which means density is simply how much mass you pack into a given volume of the fluid. But fluids are more than just shapeshifters. They also have a personality when it comes to flow. They resist flowing sometimes. This resistance is called viscosity, and they can be squished a bit under pressure, which we call compressibility. Both of these depend on how the molecules interact inside the fluid. So, next time you pour syrup on your pancakes or watch steam rise from a cup of tea, remember, you're seeing the marvelous dance of molecular forces that make fluids so unique. Imagine you're diving into a swimming pool. The deeper you go, the more your ears pop. That's pressure in action, a fundamental concept in fluids. Let's start with the basics. Pressure is the normal force applied per unit area. Think of it as how hard the fluid is pushing straight on a surface. And here's the cool part: it pushes equally in all directions at any point inside a fluid at rest. To picture this, imagine a tiny balloon immersed underwater. The water pushes on it evenly from all sides. The mathematical expression for pressure is P equals F perpendicular divided by A. That means pressure equals the force acting at a right angle to the surface divided by the area over which this force is spread. You might wonder, if force is a vector with direction, why is pressure a scalar? That's because pressure in fluids is isotropic. It transmits equally in every direction at a point, so it doesn't have a specific direction itself. The C unit for pressure is Pascal, abbreviated as Pa, where 1 Pascal is equal to 1 Newton per square meter. Pascal is named after Blaise Pascal, a guy who literally changed how we think about pressure. Also, atmospheric pressure, the pressure exerted by the air around us, decreases as we go up a mountain or fly in a plane. This concept isn't just academic, it helps explain everything from why your soda bottle might pop open at high altitudes to how weather patterns form. Density is like the fingerprint of a fluid. It tells you how tightly packed its molecules are. By definition, density, denoted as ρ, is mass divided by volume. But remember, density doesn't stay constant, it changes with temperature and pressure, kind of like how things expand or contract when they get hot or cold. Now, here's a handy concept called specific gravity. Specific gravity is a ratio comparing the density of any substance to the density of water at 4 degrees Celsius, which is when water is at its densest. The formula goes: specific gravity equals the density of the substance divided by the density of water. Because water's density at this temperature is exactly 1000 kilograms per cubic meter, specific gravity ends up being a dimensionless number, no units. Why is this useful? Well, materials with a high specific gravity are heavier for the same volume and exert higher pressure at a given depth. This influences how things float or sink, which is critical in hydrostatics. Think ships, submarines, or even your own buoyancy when you swim. Gravity is like the boss of fluids at rest. It decides how pressure behaves under its watch. When a fluid just sits quietly under gravity, pressure increases as you go deeper because the fluid above presses down with its weight. The pressure difference between two depths is given by delta P equals rho times G times H. In words, the change in pressure equals the density of the fluid multiplied by acceleration due to gravity times the depth below the surface. So, pressure depends on how deep you are, not on the shape or size of the container holding the fluid. This principle is why dams are thicker at the bottom, why hydraulic lifts can work so well, and how manometers measure pressure. It's as if gravity stacks the fluid in layers, each adding to the weight below, pushing harder the deeper you go. Let's picture fluid pressure through a graph, a pressure versus depth curve. For an incompressible fluid like water, this curve is a straight line going upwards, meaning pressure increases linearly with depth. The formula is P equals P naught plus rho times G times H, which means the pressure at any depth is equal to the pressure at the surface plus density times gravity times depth. Here, the base pressure depends on the fluid's density, gravity, and how far you've submerged into the fluid, assuming gravity stays constant over that vertical range. But what if the fluid is compressible? Take gases high up in the atmosphere, things get tricky, and the linear relationship breaks down because air density changes with altitude. The model we just described assumes no temperature changes or compressibility in the fluid column, which works well for liquids but needs refinement for gases. So, this simple linear model helps us understand pressures deep underwater or inside tanks, but nature spices things up when compressibility kicks in. Let's wrap up today's introduction to fluids with some key formulas and concepts. Density, which we say as rho, equals mass divided by volume. This tells us how heavy a fluid is for its size. Pressure, P, equals the normal force perpendicular to a surface divided by the area over which it acts. The pressure difference with depth, delta P, equals density times gravity times depth, showing pressure increases as we go deeper under fluid. Specific gravity is the ratio of a substance's density to that of water, helping us compare densities without worrying about units. Remember, fluids flow and don't have a fixed shape, with mechanical properties centered on pressure, density, and compressibility. Pressure in fluids at rest pushes equally in every direction and rises linearly with depth, which is why dams hold back water and why your ears pop underwater. Specific gravity helps us understand buoyancy and many hydrostatic calculations. That's it for today's concept. Physics is fun when you can laugh and learn. See you in the next session.